Hello and welcome to the internal combustion engine progress presentation for Lab Section 8, Group 4, Graham Brantley, Marley Miller, Anderson Page, and Sam Pendergast. For this lab section, we've been hired by Generative Energy Systems to determine the parameters and controls for a new internal combustion engine system that they have provided. Now, our main goals for this project are to first accurately model the system, most importantly, understanding all of the components of the work energy balance equation, which we'll be investigating later in the presentation. And once that system is understood, we will then attempt to maximize the power output from the system using compressed air to simulate the combustion of gas in a standard internal combustion engine. For this presentation specifically, we will begin by speaking about the system anatomy and background for the equipment we'll be using in the lab, then discussing the calibration sequence and the equations for both calibration and the lab itself. Next, we will look at determining the mechanical properties of the IC engine and the work energy equation. Finally, we will characterize the full four-stroke cycle of the engine. The system anatomy, our first photo here shows the system as it will be run the first set of experiments without the engine head, with the cylinder and piston exposed as shown. Another important component here is the flywheel, which is attached to the crankshaft and the piston. The weights on the flywheel can be altered, which allows us to change the inertia of the flywheel. By changing the inertia of the flywheel and running the engine at a number of different angular velocities, we can characterize the system for a number of parameters. Next, we have our calibration setup. This will be discussed further in the next slide. However, one can see the force transducer as well as the two moment arms that will be used. Here we have the angular encoder, which will record the angular velocity and position of the crankshaft and therefore the piston. It will also be used to calculate the angular displacement. We also have the coupling used to connect the electric motor to the IC engine. And finally, we have the engine head and valves attached to the IC engine. This is how the system will be run for the second and third parts of the lab section.
In order to be able to measure the torque output of our engine, we used a force transducer a known distance away from the engine's central axis of rotation, which measured a force F equal to the torque produced by the motor divided by our moment arm length. However, before we could use our force transducer to characterize our engine, we needed to calibrate it. We did this by incrementally placing and then incrementally removing known masses on the left side of the moment arm as shown, creating resultant forces of a known value at the transducer that were then measured. By plotting our applied torque against the voltage measured by the force transducer, we were able to use a York regression and obtain the calibration curve shown. This fit appears to be very poor, but upon further inspection it became clear that all of the points on the left side of the regression line were taken while masses were being added, and all of the points on the right side of the line were taken while masses were being removed. This is an example of hysteresis, or different behavior depending on the direction in which a value is approached. This hysteresis is inherent to our experimental setup and cannot be removed. Since the rotation of our engine will always produce cyclic loading patterns for our force transducer to measure, we are unable to calibrate around this hysteresis and have to simply acknowledge the error it introduces. The purpose of our experiment is to model our engine system through the shown work energy balance equation. The first term in this equation represents the change in kinetic energy of our flywheel, the disk that our engine is designed to spin. It is calculated from the moment of inertia of our system and the change in angular velocity of the flywheel. The second term is the work done by the motor on the flywheel to get it to move. The third term is the work done by the compressing and expanding air on the piston and therefore the flywheel. The fourth term is the work done by friction throughout the system. The fifth term is the work done by the air that is injected into the expansion stroke of the engine to simulate combustion. The sixth and final term represents the extra work that is unaccounted for by our model. We would like to calculate each of these terms in order to characterize our engine system. We began by trying to find the moment of inertia of our system so that we could determine the kinetic energy term of our equation. By removing our piston head, we prevented the compression and expansion of air from doing any work on our system. Additionally, we did not inject air into our piston chamber. Finally, we assumed that the W discrepancy term was negligible. This yielded the new equation outlined in green. By running the motor at steady state, the kinetic energy term was set to 0, and the work done by friction was calculated. By then using the motor to increase the angular velocity of the flywheel, the moment of inertia of the flywheel system could be found.
The next step is isolating the work done by air. In order to isolate the work of air term in the energy balance equation, the engine is run with the head bolted back on. In this condition, with no air injection to power the engine, and assuming the discrepancy is still negligible, the work of the piston is still equal to 0, and the work of air can be found by analyzing steady-state data. Steady-state data was collected for 3 speeds with 4 masses on the flywheel, and then again with no mass on the flywheel. When analyzing this data, the work of air can be found during the compression stroke from 180 to 360 degrees, and should be approximately equal to the work of air during the expansion stroke from 360 to 540 degrees. The work that has yet to be done is the optimization of the power output of the engine. This will require investigating the optimal time and duration to inject air into the cylinder to get the most work out of the piston. If air is injected too early, it will work against the piston, and if too little air is injected or it is injected too late, it will not generate work. In order to measure the work being generated, the engine will now be powering the motor instead of the other way around. The timing and duration of injection, as well as the measurement of power output, is all controlled through the LabVIEW VI. Additionally, the discrepancy of work term that was assumed to be negligible must now be characterized in order to see how much error can be expected in the max power output.
As previously mentioned in the Step 1 process slides, by setting W air, W piston, and W discrepancy equal to 0, we're able to isolate an equation capable of solving for the inertia of the system. By varying the number of flywheels and the steady-state angular velocities, we're able to create a function defining inertia with relation to the number of flywheels. The number of flywheels in the equation is denoted by the variable n. This equation takes the inherent inertia of the internal mechanisms of the engine into account. The inherent inertia was calculated by noting the relationship between additional masses and varying speed to the inertia calculation. Since we were only able to vary the weights externally, we compared the collected data to one another to find their intersection, this being the internal inertia of the engine, as shown in the intercept portion of the equation. Variability in the inertia equation was calculated by a York regression and is shown with the plus or minus sign in the slope and intercept terms. As discussed in the Step 2 process slide, we can attach the motor head onto the system to characterize W air. Again, W piston and W discrepancy are assumed to be 0. Note, we have left W discrepancy in the simplified equation because although it is assumed to be negligible, it still technically exists and will be calculated in Step 3. We can analyze this information by looking at the encoder data and categorize the work done by air to occur during the compression stroke of the engine. For the frame of reference seen in the example graph, we can calculate the area under the curve between angles 3,780 and 3,960 degrees to get an approximation of W air. Also note that this area calculation occurs between the curve and the x-axis. As you can see, this value will be negative. The data we collected was very noisy, so as mentioned in the title of the graph, the torque data has been averaged to be more readable. We're able to determine the uncertainty of our calculations by comparing the experimentally calculated W air and the theoretical one. Finally, here we have cited the references we used thus far, these being the lab guidance manual and the equation sheet provided by the professors.